Okay, so today again we are going to talk about ray tracing, right? Looking at the interface from the user's point of view, just like what we did in viewing transformation. So if we recall what we see in the 3D viewing interface, so what we had was that the scene was basically defined in word coordinate system, and the eye or the viewer was specified, or the camera was specified in another coordinate system, which was viewing coordinate system, right? And in fact, this was a left-handed system and this was a right-handed system, right? So let's say if we assume that this is the kind of interface we are going to have from the user's point of view. That means user is going to specify the position of the eye or the camera in this coordinate system, and your word is going to be in this coordinate system, right? So there are going to be issues in terms of how do we specify the corresponding ray definition in one of these coordinate systems, so that when we get the intersection of the ray with the word, this is consistent with the coordinate system, right? So we need to look at the issues of, again, the transformation from one system to another system, right? And how do we incorporate that with respect to ray tracing? So now, so what do we have here again is, this is the eye, right? That's where the origin of the ray starts, right, with respect to the ray tracing. And this is what we get as our viewing volume, right? So we need to have this in one coordinate system, right? So whatever scene we specify here in the viewing volume has to be in the same coordinate system. Now the question is that, would you like the ray to be specified in the word to have the intersection done, right? That is one way, but we are insisting that the specification of the eye is in another coordinate system, right? So we need to transform that into the word coordinate system, so that the intersection what we get is in the word coordinate system, right? The other issue is that one could have done, let's say, this whole process of finding the intersection and so on in viewing coordinate system, right? So what is the implication of that? At times what happens is that one aspect is to get the intersection point, right? Another aspect is to get the normal at that point. So at times we are given even the normals for the object, or let's say the faces or the polygons of the object, right? So not only just the coordinates of the vertices are given, but also the normals are given, right? So that one doesn't have to compute them. So in that situation, we would like to use that information which is already there, rather than recomputing them. But again, these normals are in word coordinate system. So therefore, it is better to do this intersection in word coordinate system. Fine. So what are we saying here? Again, recapitulating some of the issues with respect to the viewing transformation. So if this point P, which has been now transformed in UVN or the viewing coordinate system, and if I consider a ray coming from the point E, which is the eye, then this is the point which is of interest, right, which is on the image plane, right, and that's what I would render here. Fine. So again, I can see this as a ray defined in a parametric form, right, with origin as E and this point P as the termination of that, right. So the same thing can be represented as a line parametrically like this, right. and we have a similar definition of the ray. So, there is a match, right. Okay.
So, I is in the viewing coordinate system?
Right. So, this I is in the viewing coordinate system. Right. So, this is I am defining it in this coordinate system, just looking at the definition of a line with respect to the point defined E and this point which I have got after having done the transformation from the word to the I, right. Okay, and that is where I get the image of the point. Okay, so, we have implicitly already seen what ray tracing is doing when we were doing transformation, right. Okay. So, then the question is, now we have understood that we need to have the mechanism of transforming a point from one coordinate system to another coordinate system, and we have debated on that it is better to have a point represented or the ray represented in word coordinate system, right. So, let us say if we consider a point defined, let us say x, y, z in word coordinate system, and correspondingly the point is a, b, c in viewing coordinate system, then what is the transformation which takes the point from one system to another system, right. So, we have seen it earlier. If this is the point P we are considering, then all it requires is a transformation of the type M, right, which is the submatrix, topmost submatrix of the 4 by 4 matrix, and then there is a offset term or the translation term R, right. And if I am interested in getting ABC, given I know M and R from x, y, z, I can obtain in this way, right. So, therefore, I can get this ABC from the point given in the word using this, right, because this inverse of M happens to be the transpose, right, just because we know M is basically formed by the u, v and n vectors, right, which are nothing but these, right, that we have already seen it, and this is nothing but a matrix which is orthogonal, and therefore, the inverse of this is the same as the transpose. Fine. Okay. So, basically we can get a point in the viewing or the I coordinate system from the word. That is what we have done. Okay. So, now the question comes, how does this map to our ray tracer, right. So, what are we saying, that if we have to take the definition of the ray which is coming from the specification of I in the I coordinate system to the word coordinate system, right, that is what we want. So, if we want to have this setup for the ray tracing, what are the steps we need? The first thing which we require is the definition of the viewing reference point, which in turn defines this offset, the R, right. That is a user specified quantity, right. So, you either compute in some sense this VRP or give VRP, right. So, this is a user specified, and we obtain the matrix M from U, V and N, and we know how to get these U, V, N, right. You have done it in your assignment, right. So, there is a way you can either specify or get N, right, and then there is a way you align the V vector in conformation to the up vector which is specified by the user, and from these two you get U, right. So, we can obtain the matrix M. So, now if the I, which is defined in, let us say, viewing coordinate system as E, given as EU, EV and EN, right, which is typically defined as a point on the line of sight, right, where the line of sight is coincident to the vector n, right, then typically we observe that the I is defined as 0 0 minus E, right. Now, what we are looking at is that where does this point go in the world coordinate system, right. So, all we need to do is perform the transformation of this through M and R and obtain I in world coordinate system. Fine. So, we now know the position of I in world coordinate system, right. The other thing is we need to also look at the definition of the window, which might be in again the viewing coordinate system and the corresponding pixel location to the world coordinates, right. Okay. So, what are we saying here? So, let us say this is the I E in viewing coordinate system through 0 0 minus E, right, and these are the objects. This is the viewing plane where the window is specified through W L W R along U and W B W T along V, right. These are just the extents of your viewing or the window, right. So, typically when you specify the zone of the screen which you want to render, so you would specify what are the pixels, let us say along x or the horizontal axis, and what are the pixels in the vertical axis, right. This is typically you will define the region or the zone of the window through pixels basically, right. So, let us say this is how we specify that we are looking at these many rows and these many columns on the screen which we want to render, right. What is the number of pixels we want to render in horizontal axis and what is the number of pixels in the vertical axis, that window, right. So, window is defined as pixel array, right. So, now the question becomes for a pixel which is located at I jth location in this array would correspond to a point U I V j n 0, right. Let us assume that this is at n equals to 0, the viewing plane, fine. So, then it is just a matter of figuring out what are U I and V j, right. So, I can compute this U I and V j through W L and W T, right. So, just a matter of mapping this into the window size which is defined through W's, W L, W R, W B and W T, right. So, that is how it is done here, right. So, it is a W L plus J I delta U and V j is W T minus J times delta V, where delta U and delta V are defined through this, right. Simple, nothing very complicated, right. All is it doing is basically locating the pixel in this coordinate system, right. Now, what do we have to do? We have to define ray. So, the point of the origin through I has been defined of the ray, but we have to define the direction now, and that is where the role of U I V j comes in, because that is where it is passing through and that defines the direction of the ray, right. So, what do? We basically look at the parametric equation of ray through the point of the origin which is I. There is a direction which corresponds to the I jth pixel, right. and this is the parameter t. Right. So, same as R0 RDT form. Right. So, now I we have already figured out. How do we get I given the I point in viewing coordinate system? The direction is nothing but the pixel position minus E, which is the I position in viewing coordinate system, transformed through M. Right. So, since it is a direction, I do not need R. Right. So, this way I get direction I j, which is in case if I am considering I to be 0 0 minus E, that means along the axis n, then all I get direction I j as u I v j E transformed through M. Right. So, therefore, now the ray is defined in word coordinate system. That is what we were trying to achieve, right, and which is in the same format which we have been looking at for performing the intersections. Right. So, then next steps to be considered are fairly straightforward. All you need to do is find intersection with the object, that let us say give you the point here as R I, find the normal at R I as some R n, right, find intensity I at the point, right, which is nothing but applying illumination model, right, and then find the pixel color. So, what may happen is that when you are computing this I, it may give you a certain range, right. So, one thing is this I is a scalar value where you are rendering a grayscale kind of an image, right, single color image with tones of intensity, or it could also be a color vector having components of RGB, right. So, then you have a colored image, right, and there could be a certain range which you get it for your image, right, which you may require to remap to a certain range of your device color maps, right. So, some I min I max of this could then be mapped into some, let us say 0 to 255 or whatever range you have for the depth of pixels in your system, right. So, that way you decide the final color of the pixel, fine. So, this is how the whole setup is done for ray tracing, right. So, you are all set for writing your own ray tracer, right. Yeah. So, what we have done is only one level of ray tracing, right, in the sense that we are not looking at the secondary rays, right, just a intersection of the ray which starts from the eye and hits the object, or let us say series of objects, and then you consider the frontmost object to be rendered, right. Now, there is an interesting issue here is that so far what we have looked at in terms of objects are fairly simple objects, right. Now, it might be useful to see if there could be objects which could be derived from those simpler objects, right, without doing too much and still be able to use your ray tracing, right. So, what are we referring to? Let us say, but this is particularly relevant if I am using, let us say, a description of a hierarchical scene, right, where the instance of an object is obtained applying a modeling transformation to a primitive, right, then I know how to handle that primitive, which could be one of those simple primitives like sphere, plane and things like that, which we have dealt with, right, for ray object intersection. Then the question is, when I have performed a modeling transformation to those primitives, can I still be able to can I still use the ray tracing without adding too much of a problem? Okay, let me illustrate this problem. So, what I am referring to is that, let us say we are transforming objects. Transforming objects means we apply a modeling transformation to an object. An object, when we say, is some sort of a simpler primitive which we know how to deal with respect to ray object intersection, right. So, what are we saying is that, let us say if I look at the ray as a parametric defined line which is S plus C t, right, and the objects which we have already looked at are of the kind sphere, plane, box, cone, etc., right. So, let us say we call these to be some sort of a generic or a normalized class of objects or primitives, right. So, for instance, if I am dealing with an object which is a normalized sphere in the form x square plus y square plus z square is equal to 1, then I know that finding intersection is relatively simple. We have dealt with it, right. Now, the question which is being imposed is that if I take now this sphere, right, and perform a transformation to this, right, how does the ray tracing change? Okay, that is the question we are trying to address. So, that is where I said that this is particularly pertinent if we have hierarchical description of a scene, right, where we would like to have instances of a simple primitive using modeling transformation, right. Then the question is, can we still handle the ray object intersection in the same way, right. So, let us say that the kind of transformations we are trying to absorb are affine transformations. Okay. The class of transformation which we want to deal are affine transformations. So, if we see that these affine transformations are applied to these simple primitives, what change do we need to be able to perform those ray object intersections, right, so that we can incorporate them, right. That is the question we are trying to answer. Any suggestions?
Sir, the point of intersection of the ray with the object will also undergo the same transformation.
The point of right. So, what do we do? See, we know how to handle the ray intersection with, let us say, a sphere which is normalized in the form of x square plus y square plus z square equals to 1. Now, I have some transformed shape, right, which has been applied on the sphere. So, right, and I know this transformation, okay, and my interest is to find out now ray intersection with this transformed object, right, because that is what I am going to render.
So why don't we change our whole scene into the, with this transformation? Now we can apply the
Yeah, but how do we find the ray object transformation? The object when transformed is not anymore this simple primitive. Therefore, I cannot apply. So, let us say if you have already written a ray sphere intersection routine which is dealing with only the simple normalized form of sphere, right, and I still want to use the same routine.
So to the output of that you apply this transformation to the point of intersection. We need not recompute the point of intersection.
Yeah, so something has to be done there, right?
We apply the same concept.
So, let us see, let me elaborate on here. So, what are we saying? Let us say I have a sphere here, right, and I perform a transformation through T, that is the transformation I have, and since I am talking about the class of transformation as a fine transformation, I can see this to be a composition of, let us say, submatrix M, a matrix M which is linear transformation, and there is some translation D, right, which would give or make this object sphere transformed in this way, right. Now, the fact that I have this transformation known to me, I also know the inverse of this transformation, or I can know the inverse of this transformation, right, which is T inverse, which is nothing but M inverse and minus T, right. So, from here I can go back here, I know that, right. So, what we are saying is that if I have a point here as q prime for the sphere, then I know the corresponding point q through this transformation T, right, as this q is equal to q prime M plus T, right. So, now when I look at what happens to the ray, right. So, my definition of the ray is some S plus C T, right. And so, this is the ray I have, which has been computed by all your setup, right, in word coordinate system or whatever coordinate system you are using, right. And so, let us say this would be the point of intersection P with this ray of this object, right. So, all I need to know is what point it corresponds to here, right. And in other words, what ray I have which would give me the point P prime which corresponds to the point P. That is all I need. See, I need to render the point P, which is a consequence of the ray intersection defined ray as S plus C T to this object, right. And unfortunately, I do not know how to compute intersection with this object, right. What I know is how to compute intersection with this object, right. So, the trick here is that I would like to get the corresponding ray to this, right, which would give me the point of intersection P prime corresponding to the point P here. That is what I am interested in. Is it okay? So, what are we saying, that the corresponding ray in this for this object, which I define it at say S prime plus C prime T, right, is nothing but the inverse of the transformation which I would apply to this ray, which is m minus, right, because it's just a ray, it's a vector direction, right. Is this fine? Okay. So, then it is just a matter of comparing the coefficients of the two sides and figure out what is S prime and what is C prime. So, in a way I have obtained the corresponding ray for this primitive, right. Now, this newly obtained ray, right, can be now fed to the standard routine I have for ray sphere intersection, right, and then I obtain the point P to be rendered. Fine. Now there is still a problem.
Can we say that P and P prime corresponds to the same transformed points?
Exactly, that's what we are saying. See, if we
You just transform the ray.
yeah, now we are transforming the ray instead.
Yeah, but how will it ensure that the new ray point of intersection with the sphere is this P prime?
That's what it is.
Scalar point transform.
See, what did we say? We said this, right? That there is a point Q here in this object, which has a corresponding point Q prime in this object through the transformation T. So I can always map Q prime to Q or vice versa, right? That's precisely what we want to do, right? And that is done using transformation of the ray, right? Okay. So, but now there is still some problem, right? What is that? We have obtained the point of intersection. That means we know what point to render. But there is something else required. Normal. How do we handle that? That was your question in minor. Right? So, what is the answer? Okay. So, the problem you have understood that we have been able to do the transformation to the object. Now, we need to have the, or let us say the question is, can we obtain a transformation which would necessarily be applied to the normal without recomputation of the normal of the deformed or the transformed object, right. So, what we are saying is that we need these normals, right, to be able to render them for the transformed object. Now, the question is, can the normal be computed using the old normal, right, and the transformation? Right, that is the question we are trying to answer. So, what is the transformation which takes, let us say, normal defined for the primitive, normalized primitive, to give us n prime, which is the normal of the transformed object. So, that is what we want to know. Right. So, at first sight you may say that it is the same as, but unfortunately that is not true, right. So, what is happening is that if I consider, let us say, 2 points P A and P B, which are very close to each other, so it could be applied to any object, right. So, we are not specifying the type of the object. So, these are the points which are very close enough, then they basically define the tangent at that point, right. So, that is why they need to be close enough. So, if I have P A and P B 2 points which are close enough, then the condition which needs to be satisfied for the normal is nothing but the dot product with this has to be 0, right. Now, this can be rewritten in this format if I consider, let us say, a point being defined as a row, right. All I need to have a transpose here, right. Now, what we are saying is that we apply a transformation T, which is consisting of the component M and D, which would get applied to P and P B, right, when we apply that to the object, right, which in turn would give you the transformation as P A minus P B times M, right. And so, keeping the same condition here, that the tangent and the normal give you 0 as a dot product, same thing is here. So, this is for the transformed points, right, or they give you a transformed tangent. And let us say if I define n prime to be the new normal, right, I just use that n prime. So, this also should give me 0, right. So, now getting n prime is what the problem is, right. So, basically we are looking at the solution for n prime, right, through this. Now, let us say if I define capital N to be the transformation which is required from the normal n, which was for the object which was not transformed, to n prime, which is the normal of the transformed point. So, this is the transformation n, capital N, right. So, I am just substituting here, instead of n prime I just substituted as n times capital N, right. So, this gives me this, right, P A minus P B M n transpose small n transpose equals to 0, right. So, this holds true when I have n transpose to be the inverse of M, right. Therefore, n, which is the transformation I am looking for, is nothing but M inverse transpose, right. So, you have the solution of your question here.
So this is M itself.
Sorry, how is it M itself?
So M is an affine transformation.
So, that the inverse of that is not the transpose, sorry. If it is orthogonal, then it is okay. And that makes sense. See, if you have a rigid transformation, rotation, right, and then if you apply that transformation to the object, then the same transformation would get applied. Right. Is this okay? Or let us say if I give you a simple example, maybe. So, what we are saying is in 2D, this is some plane, right. The normal of this is this, right. And now I give some kind of a scaling in one direction, right. So, clearly it is not the same transformation which will get applied to the normal. If I do that, the normal is going in a something like this, right, whereas I have the normal now this, right. So, but that is a powerful thing, right. Now, you can handle transformation applied to the simple primitives, and therefore, you can construct much more interesting scenes rather than just having these unit spheres and planes and so on and so forth, right. Fine. So, maybe we stop here now and we will continue on the recursive ray tracing next time.
It's a line.
So it's not in every case it won't be a line. Is it generic?
Tangent.
Yeah, see, this is just a matter of defining a tangent, like difference of 2 points close enough. It's a tangent vector.
Is it in 3D is a plane?
Yeah, so see what will happen, it will have two components, one will be in this direction, another will be in another direction, two tangents, and the orthogonality holds with both of the normal, right. See, whatever vector I have in that tangent plane, the orthonormality holds, therefore the dot product is 0.
So can you go back slide?
Yeah.
So one more. So what is d s minus d into m?
See, d is the offset. When we are dealing with the affine transformation, right. So, let me just go back one more. So, if I define this T using this M matrix, right, which is the linear transformation part, right, and D is the offset of the translation which I may apply. So, that in combination gives me the affine transformation, right. So, if I am talking about 4 by 4 matrix in a 3D case, right, then the topmost 3 by 3 submatrix is this M, right. Any other question? Okay, so we stop here, and next time we continue on recursive ray tracing, right. There we would like to also consider the secondary rays, right, rays due to reflection, rays due to refraction, right. Shadow rays we have seen, but the effect of those to the computation of illumination, that also we would like to see, right. If we detect that the point is actually under shadow, what happens to the illumination, what kind of illumination you would use, right. So, all these we will talk next time. Thank you.